Check one. All right. Good morning, ladies and gentlemen. We are delaying for about a few minutes because of a technical issue. Please bear with us. We will come in shortly. Thank you.
Okay.
Good morning, ladies and gentlemen, esteemed guests, distinguished guests. It's so wonderful to have you all with us today. Welcome to ICIIT Conclave 2024, where we gather to explore the innovative world of generative AI and large language models. Today, we stand at the intersection of innovation and imagination, where artificial intelligence meets human creativity, transforming industries and redefining possibilities. I'm Tarinder.
And I'm Pramudi.
And we will be your hosts for today. Informatics Institute of Technology initiated ICIIT conference in 2016. Although this was paused for several years, we were able to resume this initiative over the last 2 years. And now we are back with a new novel approach.
This year, we have rebranded this event as a conclave to bring together like-minded people from across state and private universities, as well as industries, focusing on large language models and generative AI. This event marks a significant evolution from our traditional annual conference, reflecting our commitment to greater collaboration and innovation. As we embark on this journey, let us reflect on the remarkable progress we've witnessed in the recent years. Generative AI, a field once confined to the realms of science fiction, is now a driving force behind groundbreaking advancements. From generating stunning artwork to composing music, to writing coherent and insightful essays, AI is not just a tool, but rather a creative partner. Large language models, such as the renowned ChatGPT-4, exemplify this revolution. Trained on vast and diverse data sets, these models have demonstrated an unparalleled understanding of language, enabling them to perform tasks ranging from translation to summarization to complex problem solving. They are reshaping how we interact with technology and each other.
As we dive into today's discussions, panels, and presentations, let us embrace the spirit of innovation and collaboration. Together, we can harness the transformative power of generative AI and large language models to create a better, more connected, and more intelligent world. We are proud to have submissions from multiple universities, state universities, as well as private universities, and also from industry leaders for today's event. Thank you for being here, and let's make this conclave an unforgettable experience. Let's embark on this exciting journey into the future of artificial intelligence.
Our keynote speaker, Dr. Romesh Ranavana, chairperson of the AI Strategy Committee for Sri Lanka, has joined us despite his busy schedule. We also welcome Professor Nirmali Veeratunga's team from Robert Gordon University, who will share their research in an invited talk. Following the inauguration session, we will be having 2 breakout sessions. These sessions will feature 10-minute presentations on real-world applications of large language models, followed by 5-minute Q&A sessions, as our goal is to foster interaction and collaboration, setting this conclave apart from traditional conferences.
To kick things off for today's event, it's our honor to introduce the chair of the conclave, Dr. Ruan Veerasinghe, Dean of Academics at IIT. Dr. Ruan was a former director at the University of Colombo School of Computing from 2004 to 2010. He is a resolute researcher and academic, deeply involved in educational reform and innovative content delivery. Dr. Ruan's work in human language processing aims to increase accessibility to information for all, particularly through machine translation to bridge the gap between Sinhala and Tamil languages.
He completed his schooling in St. Thomas's College, earned his bachelor's in mathematics and statistics at the University of Colombo, and received his master's and PhD from the University of Cardiff in the UK. Dr. Ruan will now deliver the inaugural speech, explaining the purpose of the ICIIT Conclave and the thought process behind its creation. Later, he will also moderate the panel discussion. Please join us in welcoming Dr. Ruan Veerasinghe to the stage.
Thank you, Tarind and Pamdi. Welcome to this ICIIT Conclave. I think the ICIIT brand has been there for several years, as they mentioned. And as they mentioned, we've kind of turned this around from a generic IT conference to something that brings, that builds a platform for people who are like-minded to collaborate. And so the term conclave comes from, I think, from a religious background, you know, where people elect a pope or something like that. Yeah. So we are going to elect something like that in the LLM space. Some months ago, some of us at IIT, led by our CEO who has just walked in, Mohan, Fernando, we looked at, you know, what should we be doing in this annual event. And we saw that from two kind of fronts. One is this whole idea of not having a conference that, where we present our work only, but one that is a platform where people from all universities as well as the industry come together. The second one is, of course, that Mohan was very serious about this. This shouldn't be a one-off event. We just come, meet and eat and all that and go, and then that's it. But it should have something that comes after it. And so I'm happy to announce that at least on one front, in a shared task that we did yesterday for building a Sinhala large language model, that group has decided, no, we want to meet again in 3 months, not in 1 year. And so we also have an offer for hosting that in about 4 months' time. So clearly we are at our early stage. We have only a few industry and state university people yet with us, but I think we are beginning a journey, and in the years to come, hopefully, this will bring people, like-minded people from academia and industry together to deliberate on these issues. Somebody asked me, so next year, what is the topic? I said, I don't know. We don't know what the topic is going to be, right? But I'm also very happy that we have Dr. Romesh Ranamana, as they announced, who is the chair of Sri Lanka's Presidential Committee on Developing an AI Strategy and Policy. He's an academic turned entrepreneur, technopreneur, I guess. So he's having a lot of experience from different areas, and we are looking forward to his keynote. We are also happy to welcome our collaborators from Robert Gordon University, led by Professor Nirmali Veeratunga, who will be sharing some of the work that they have done and some of the recent work we have been doing together. And then we have to thank all those of you who have come from industry and other universities who are going to share what you're doing currently in the sessions that follow tea. And then finally, later in the afternoon, we will have a panel discussion again with some of our visitors as well as people from the industry. So I hope that this will not be just a talk shop where we make some presentations go, but we will interact. All the post-tea sessions are of 10 minutes, and for 5 minutes we will have Q&A. And I hope you have a lot of questions to ask. Unfortunately, Romesh has to go very early, but he's willing to take a few questions soon after his talk, and maybe the same with Nirmali and Stuart. So with that, let me welcome you to the ICIIT Conclave, and wish that we all have a very positive experience and something that will not stop after today. Thank you.
Thank you, Dr. Ruan. Now it is our pleasure to introduce the next speaker, Mr. Mohan Fernando, the Group CEO of the Informatics Group. Mr. Mohan has a distinguished career, having served as a principal consultant and head of global operations for an IT company.
Mr. Fernando holds a bachelor's in mathematics and computer science from the University of Peradeniya, a postgraduate diploma in applied statistics from the University of Colombo, and a master's in applied psychology from the University of Coventry, UK. Today, Mr. Fernando will speak about IIT and our involvement in AI-based research. Please join us in welcoming Mr. Mohan Fernando to the stage.
Good morning, everyone. It's a difficult speech when you have to speak right after the same person that you planned the whole year for this event, who already revealed what we discussed. Yeah, but I'll try to make an effort. So This is the third day in a row that we have the research gathering. But if you look around in terms of numbers, this is the smallest. Yeah. So last year we had, was it Kingsbury we had last year? Yeah. No, Kaladari last year, Kingsbury. So we had like probably 300 participants, a normal format of a research conference. So, so this is a drastic difference if you look at from the venue and the format of it. If you think like, oh, did you have time to plan? No, it's exactly the opposite. Because this time we started planning much earlier than every other year so far. Then we discuss in length what we are doing with the conference, why we are doing it. And there are many conferences here in Sri Lanka, happening in Colombo. Almost every university is having one, probably 15 plus conferences each year on various topics. And we could be the 15 plus one. So this all started with one brainstorming session with Ruan. We very seriously spoke, probably till very late that day. Do we have to be that 15 plus one conference? And we thought, no, we shouldn't. That's also in line with what we are trying to drive as a vision at IIT. First, to be different. And the second one, not to be a number, but to make an impact. So we made a conscious decision, of course, with a lot of risk. What will everybody think when we change the conference, a big conference, into a conclave? So this word is very carefully selected. It's not random. We struggle with the word. We wanted to call a meetup. It's actually the point. It's actually the concept. We wanted all the like-minded people to meet up, have a conversation, and make progress, and to make an impact. That's the whole objective of this. Since meetup would have sounded a bit casual, we came up with a slightly posh word, say conclave. But the whole idea is still the meetup. But then the numbers. If you see, we didn't advertise this event, at least not mass. There's a reason for that. If you are here, that is because we wanted you to be here. We didn't want anybody else randomly sitting here today. Why? Because we don't want the people discussions to be distracted if they're not interested on the topic. So you are here because you have a keen interest on the topic, and we all hope throughout the day you will all have a meaningful conversation and contribute to that. That's why you are here. That's why this number. So each seat is carefully selected. It was a painstaking job for Dr. Ruan. We had a registration process, and we also checked whether are you seriously keen about LLM, because we didn't want to waste anybody's time. It's going to be a very boring session for the others, but extremely intriguing session for those who are in the subject, those who are keen to make progress. So that's the first question answered. Why here? Why in this format? The second one, the long-term objective. As Ruan mentioned, we seriously don't know what we're going to do next year, but we know what we're going to do tomorrow. We want to continue the discussion from today. So we started the shared task yesterday on legal LM. So teams were competing, and they had a good start, and it was very successful, not because of the task itself. Even before the end of the task, we had an invitation for the version 1.0, because yesterday it was version 0. So people have a keen interest. They said, let's continue, not in 1 year, in 3 months. That was a huge win for our objective that we want to achieve. So we want to achieve the same thing today, that you all will engage. We will all agree by the end of the day what we are going to do tomorrow for for the next 365 days, 364 days. Yeah? So, as I said, this is a risk, but we like to take that, and we want to make it happen. So the whole objective is to take part and make progress, unlike once a year, throughout the year. I hope we can achieve that objective today. Welcome on board, and have a good day. Thank you.
Thank you, Mr. Mohan. We are now honored to introduce our keynote speaker, Dr. Ramesh Ranavana. Dr. Ranavana is the chairman of the National Committee to formulate an AI policy strategy for Sri Lanka, established by the President in 2023. He also served as the chairman of the SLASCOM AI Center of Excellence, contributing significantly to the development and adoption of AI in Sri Lanka. His extensive expertise has led to his involvement in various boards and committees, including the University of Colombo School of Computing and the Open University of Sri Lanka. Currently, he is the Group Chief Analytics and AI Officer at Dialog Asiata PLC, where he leads all analytics and AI initiatives.
Dr. Ranavana's career began as a co-founder, CTO, and managing director of Semicentric Technologies, and later as the CTO of Tenjri UAV. He also founded Enterprise Machine Learning Private Limited, providing strategic AI guidance to multinational organizations. He earned his bachelor's with first-class honors from University of Peradeniya, completed his PhD at the University of Oxford, UK. So please join us in welcoming Dr. Ramesh Ranavana to deliver the keynote speech.
Good morning, everybody. It's wonderful to be here, and it's really encouraging to see events of this sort being organized in Colombo, especially with all the interest that's going on AI, on generative AI at the moment. My talk today is really centered around the primary topic, which is generative AI. And I want to use this opportunity as the keynote to start the day off, to initially lay the canvas and the blueprint for what generative AI is, and within that context where large language models fit in, talk about the different flavors, the different elements of generative AI, but also give you an overview and insight into how we in industry are seeing this technology as well. How are we seeing the impact? How are we seeing the value going forward? And how generative AI especially is different to normal software development and also development of standard AI models, which has been going on for the last 20 years. How does this change the game? So really, if you look at it from the industry viewpoint, this is probably the most important graph, the most important bit of information for us. Generative AI has brought to the table the ability to simulate certain human skills which were not available with previous technology. Things like language comprehension, language understanding, doing math, reading comprehension, and over the last 20, 25 years, what we've seen is that the skill level of this AI has grown incrementally, especially at the start. Things like handwriting recognition and stuff were, hot stuff 20 years ago. In fact, my undergraduate thesis back in 2001 was actually on using handwriting, fuzzy logic for handwriting recognition. But now if you look at the level that, that type of recognition has got to, it's at a different level. But especially over the last 3-4 years, with the advent of generative AI, what we've seen is a whole bunch of new skills, especially the ability to be able to create new content, as has been mentioned earlier. Create new text, create new images, create new audio. That itself is a game changer. So if you look at how we got here, it's not an overnight change. It's basically an evolution that has happened over the last 50 years actually. What we've seen is through the advent of big data, through the digitization efforts that happened in the 90s and the early 2000s, what we've seen is we now have vast quantities of data available to us. Added to that, vast quantities of compute power. When I was doing my PhD, the only compute I had was the compute I had in my lab. And the amount of AI I could train, the amount of models, the amount of data I could use on my models, and the size of my models was limited by the amount of, essentially by how fast my processor was and how much RAM I had. But now, and even for companies, investing in AI was always very, very expensive because it required significant capital expenditure. It was very, very expensive to set up computing infrastructure. But the big game changer has been cloud technology, where you don't anymore need to invest in large computing power, and you can build as large a computer as you want by cobbling together different cloud instances and build as large a machine as you want, and then use and only pay for the amount you use. That itself is a big game changer. The next one is obviously GPUs, the ability to be able to run parallel processing jobs. I mean, I was, when I finished my PhD, my first job was working at a drug discovery company where we were developing, a drug screening platform where we were trying to identify molecules which potentially became drugs. And the first program I wrote was written on a normal CPU. At the time we had, I think, 4-core CPUs. i7 machines had just come in at that point. And for me to evaluate one molecule against a particular protein, at that time took about half an hour. And our database had about 1 million molecules. So we need to run this for about 2 months just to process one molecule. But then this was at the time when GPUs first came in and CUDA came in. And that too was a very small GPU. It had about 16 cores. But we then transferred our program to run on CUDA at that time, some of the first CUDA code. Immediately that 30 minutes was reduced to about 1 minute. And that's because what we had was all this parallel processing power, simple operations you could parallelize, and build in a whole bunch of GPUs and bring that in. So that, when you combine all this, big data, compute power, GPUs, and cloud, what we've seen is over the last few years, as more data became available, more compute became available, clouds became faster, we were able to build larger and larger models and train them on larger bits of data. And then through that, we were able to build more capability into our models. So we went from being able to do simple image recognition, identify between a cat and a dog, to now you can give an image and it will tell you exactly what type of dog it is, what the dog is doing, who is standing next to the dog, what context it is. That's the level of capability that we enable. And that's essentially an effect of being able to build larger models, train on larger amounts of data. And through that, we now have the capability to do problem solving, pattern recognition, vision, hearing, creativity, all this stuff. And this evolution has been, gradual but accelerated, especially over the last 3-4 years, with the advent of generative AI, which I'll talk about in a bit. So the recent acceleration in generative AI is fundamentally different to what we see with the types of AI that we've been using over the last say 20 years, right? So what everybody is used to is discriminative AI. Discriminative AI allows you to classify data through supervised learning. This has been done for the last 30 years, close to 30 years. And this allows you to take some data and do simple things like classification, scoring, and trained on using supervised learning. Then you also have predictive learning, which has been around for even a bit longer, where you can do forecasting. But generative AI is the new type of AI which allows you to create new content. All the other AIs allowed you to take some data and generate insights on that data. But generative AI allows you to create new contents and outputs based on the training data. So really, generative AI is a subset of AI. This is once again something that Ruan was talking to me about in the morning as well. The field of AI is a vast field. There are hundreds of different types of AI out there. Within AI, there's a subfield, which is machine learning, which you use data to train the AI. Within AI, you have deep learning. Within machine learning, you have deep learning, which is larger models. And then within deep learning, you have Gen AI. And within Gen AI, you have large language models, which is one type of generative AI. You have diffusion models, variable autoencoders, GANs, nerves, which I'll give you a brief introduction about in a bit. So if you take the field of generative AI, it's really, like I said, a subset of artificial intelligence, of creating new content from learned data, including things like text, images, music, but LLMs on their own can only do text. The larger field of generative AI, where you're talking about images, videos, it's a much larger field. There are lots of other types of models which come into that picture. So Gen AI essentially is AI which has ability to generate new content, things like images, video, art, designs, music, text. So if you take the generative AI universe, what has really led to this change is, number one, the availability of some new AI building blocks, things like transformers and attention mechanisms. This was originally, transformers were invented by Google, I think back in 2016 or 17, and then that's what has brought this whole field about. Then once you take these different building blocks, you build them into deep learning networks, and this gives you the different types of Gen AI that we have. We have large language models, diffusion models, GANs, nerves, variable autoencoders, and when you combine all those together, the new types of models that we see out there now, the multimodal models, and this eventually is what gives us the generation applications, the ability to be able to generate text, music, design, art, videos, images, all that. But it's the combination of all this that composes the field of generative AI. If you look at this from the business viewpoint, the potential impact of generative AI, especially in business, is huge. Our current estimates is that generative AI will add about $2.6 to $4.4 trillion of value to the global economy over the next 3-4 years. And that's mainly through simply automating manual human tasks which couldn't be automated using earlier technology. And then some special use cases which build on top of that as well. And this is all, all based on incremental value that we get from automating tasks, number one. And then those new use cases, the new types of applications, features, functions that companies are now able to offer to customers. And this allows us to build applications in healthcare, in finance, in entertainment, marketing and retail, manufacture, education, a whole host of different fields. Generative AI, just like all AI, is not a specialized application, it's a generic application. Which means that it can be applied to so many different fields. It's not just a one-trick pony. It can be applied to so many different things. And the use cases, like you can see in this slide, if I can zoom on this. Yeah. So this shows you, some of the impactful use cases. If you take something like banking, you have the ability to be able to apply generative AI for marketing and sales, for customer operations, for new product development, for software engineering, for supply chain, for risk and legal. This is why everybody is so excited about generative AI. The ability to apply this across the company, not for just one or two things, but across the board, from marketing to operations to new products to corporate planning to IT, you name it. So the first type of generative AI that I think most people introduced to the field of generative AI was through large language models, is the most recent catalyst to this advancement, and actually brought AI, made AI available to the general public, because they were able to interact with these AI systems using natural language. Earlier, if you wanted to, a lot of these types of AI have been around for a while, but if you wanted to work with them, if you want to interact with them, you had to go and code. And this was always the blocker. This stopped non-technical people from interacting with the systems. But generative AI, especially large language models, gave a new way to interact with complex IT systems, with complex AI systems, where you can interact with it using natural language instead of having to write a program. And this is what led to this big change in how these things work. So essentially, large language models are advanced AI systems capable of understanding and generating human language. So you send in a question and it has the ability to answer. And within that, these AIs have the ability to generate text, to do translations, to build conversational AI systems, to do sentiment analysis at a different level. Sentiment analysis for us is a big thing, especially in business, because the earlier AI models were good. They were better than not having it, but they were quite limited. We were able to classify text as being positive or negative. But now, in our companies, we are able to not just classify them as positive or negative, we classify them according to about 50 different features. Are they happy? Are they sad? We are able to use generative AI to classify, and that gives us a lot more information on what our customers are thinking. So if you take traditional NLPs, natural language processing, it relied on rule-based systems, and LLMs use deep learning and transform architectures like GPT-4, BERT to do pre-training. And that, if you look at the differences, NLPs are based on rule-based, and LLMs are based on deep learning and transformer models. There are obviously deep learning-based NLP systems as well, but if you take a lot of the traditional ones, they are pretty much rule-based, built on top of a little bit of machine learning as well. NLPs are very, very task-specific, whereas large language models use a unified model for different types of tasks. Context handling, NLPs are quite limited. If you're not capturing them in your rules, they do struggle. And we find this a lot in some of the chatbots that we build for our customers. Training process is task-specific for NLPs, whereas LLMs are more generic. You train them for multiple tasks. And the flexibility is also quite different. And over the last 3-4 years, what we've seen, I'm sure all of you have seen this graph many, many times. What we've seen is since the introduction of LLMs in around 2017, the transformer model around 2017, we had these LLMs coming in, and the LLMs have just got larger and larger and larger, and it's become like a war between all the different companies. But one of the big outcomes of, one of the big observations that we've seen within the space of LLMs is that the first LLMs were closed, were within companies, controlled by companies, but over the last 2-3 years, what we've seen is more and more of these open source models also coming into the picture, which has democratized this technology to a certain extent, but still one of the biggest barriers to usage of building LLMs and using LLMs is cost. It's especially for countries like Sri Lanka, which I'll talk about in a bit. It's very, very, it's beyond our normal purse to be able to, number one, train one of these systems, and also to use these systems to build business cases. I mean, we've been doing this at, Dialogue and several companies we are working with. We built LLM chatbots. But the problem is that in Sri Lanka, because our wages are so low, it's still cheaper to hire a call center agent to answer a call than build an LLM bot, because every time I call an LLM, it costs me 20 rupees for that call. So that's a big problem. So there's a big need for us to have smaller models which cost less. Open source models that we can train, the current commercial models are just too expensive, especially on a Sri Lankan context. Maybe in Europe, in the US, where things are a bit more expensive, you can build business cases. But in countries like Sri Lanka, it's still hard to build a business case because even inference is still, it's too expensive. So if you look at some of the state-of-the-art LLM models, You have, GPT-4, Llama 3, and they differ according to the parameter count, the accessibility, the capabilities. I won't go into these details because I think today's workshop will go into these details in more detail. But if you look at the snapshot that we look at in the LLM application universe, at least the low-hanging fruit, we are thinking of LLMs quite a bit for Q&A and chatbots, for content automation, for translation, sentiment analysis and text classification, hyper-personalization. Knowledge management is a big one, which especially in corporates, knowledge management is quite a challenge when you have these huge manuals, hundreds of manuals for different processes, and these manuals get updated all the time. It's very hard for our staff to keep up with all the changes that happen in processes and procedures. Now the new method is to put them all in a chatbot. So when somebody wants to find something, they just ask the chatbot and they're able to get the latest up-to-date information. If you look at LLMs, LLMs are really built on these three on transformers. That's the base technology, and the three main things that make LLMs and transformers so popular is that they have this inbuilt self-attention mechanism. They're able to identify which parts of a sentence are important and be able to link those together. They also built from the ground up to be parallel, to be processed parallelly, which allows us to scale these systems quite easily and build larger and larger systems. If you look at the way that these LLM models work, it's pretty simple. Most of the LLM models work in the same way. You have some way of input encoding. I'm sure all of you have used different encoding methods. And then, based on the input encoding, there's a positional encoding where it comes up with a way to encode the location of certain words in relationship to other words. Then it's sent into the transformer encoder, the self-attention mechanism. Then it's sent into a feed-forward mechanism, then the layer normalization and output layer. Once again, I don't want to go into too many technical details here. I can discuss this later if needed. But for the completeness of my talk, I just wanted to show you the architecture of these things as well. But if you look at the architecture and components, what differentiates different LLMs from each other? The model size and the number of parameters, and that has the effect on how much training data you need, how much it costs to inference, the size of the model. The input representations, the type of encoding you use. There are different attention mechanisms that different companies are using, which differentiates amongst them as well. The training objectives, the computational efficiency, and the decoding and output generation as well. If you take how these LLMs are built, you start with a foundation model. You start with the untrained LLM. You just build your LLM with the transformers cascaded into a untrained LLM. And then you obviously have to scrape vast amounts of data to build a training data set. And then when you train your data set on this vast amount of data, what you have is a foundation model, which is what all of us now use on systems like ChatGPT and all that. And what we have now is, which I showed in the previous graph, is several foundation models of different sizes and accuracy, like GPT-4, Claude, Gemini. There are lots of models out there, but they're all built using this same process. For us who are building applications on top of foundation models, there are, once again, a few methods we can use. The base foundation model, where you use the foundation model as it is, where you just ask a question from the foundation model. The second is using the internet, where you get content from the internet or give a URL to the foundation model and ask questions based on the content of that particular website. That's also becoming quite popular now. Then slightly more advanced is using RAG, where you have a separate knowledge repository, and you have a way to query knowledge from that repository and then send it into the LLM and ask questions based on that answer as well. That is what most people are now building applications on using RAG. And then slightly more advanced is when you fine-tune, when you actually go and change some of the weights of the LLM itself using particular specific training data. But fine-tuning, once again, is expensive and is a bit hard to control still. People are still learning how to properly use fine-tuning. And then the final layer is when you actually train the LLM from scratch on your own, which is, I don't think anybody in Sri Lanka has done that yet because it's very, very expensive. I mean, the last estimates for training GPT-4, I'm not sure about GPT-4, but GPT-4 was about $35 million or something like that every time you train it. So it's not easy to keep training it every day or all the time. One of the big differences also that we are seeing with LLMs is that LLMs introduce a new paradigm for how we build applications, the software development lifecycle. So if you look at how we develop software, if you look at how we develop software, the traditional way of developing software is you develop a specification, you design it, you code, you test, and you deploy. And then you have a system where you can send in a question, it gives you an answer. Machine learning, traditional machine learning, once again, has a very, very different way of development. You start with the specification design, but then the big step, and usually the most time-consuming step, is data collection. Then you also have to label the data. You have to do feature development, you have to do model training, and then you test and deploy. So that's a very, very different way of developing. Why machine learning development or AI development is different to normal software. But with LLMs, once again, it introduces a totally new paradigm on how we do this, where you, once again, as with any application, you start with specification, you design, you do some data collection, but then there is no coding or anything like that. What you do is you pre-process your data, you make it ready for the LLM or for the RAG, and then you simply do prompt engineering. And you go back and forth between refining your data and prompt engineering to build your application. So the amount of time it takes to turn around an LLM application is a fraction of what it normally takes to build a normal machine learning application. And also it allows people with much less technical knowledge the ability to be able to build these systems. Even my son is now building LLM chatbots with about one or few months of training. Now he's able to build end-to-end chat, which is really not that easy with normal machine learning development. The cost of development is also dependent on the mode and the sensitivity of your content. And that's a challenge that we in corporates face all the time. How much of the globally available LLMs can we use for our work? Because our data is then sent out into public environments, which could be then used to train their systems as well. So we are forced to look into our own methods of either hosting the models ourselves or using more private environments, which are now becoming available. So it really depends on the content type, whether you have non-sensitive content or you have personal identifiable information in your data, whether you have enterprise data, whether you need some fine-tuning. The cost increases depending on the level of security that you need. So some of the challenges related to LLMs are, one is high training costs. That's a big problem, especially in a Sri Lankan context. Fine-tuning also can be quite expensive, especially when you think of converting rupees into dollars, and the cost of inference. But also this offers some opportunities. How do those companies which are able to build sustainable business models using these LLMs are the ones which will first adopt these and be able to show a difference. And this is why training business leaders on how to build business models on LLMs is very important. It's not only about training engineers, it's also about training business leaders on how to build business model, how to identify the correct business case that's going to work with that. LLMs are not going to, you can build a nice pilot and a POC for anything, but whether that leads to a sustainable business case is a different question altogether. And that's where the business leaders also need to have an understanding of what works and what doesn't work. There's a need for smaller, cost-effective and more efficient models so that we can bring the cost down and make these LLM systems more available to people in poorer countries like Sri Lanka. And things like fine-tuning are still a bit difficult to do. People don't really understand how to do this. So I see a big void in the market for better tools, for no-code tools, low-code tools to help people with fine-tuning as well. That's also a problem going forward. So let's quickly go through some of the other generative AI models. So we start with diffusion models. Diffusion models are, I'm sure you use Stable Diffusion, you use Midjourney, you use DALL-E. The technology behind that is diffusion models. Diffusion models are a type of generative AI which primarily used for image and video generation. You start with a text prompt. Based on the text prompt, it's trained to generate a starting point for that particular image with lots of random noise, and then it iteratively refines it to get to the image that you want at the end. A process like this. And things like Stable Diffusion, DALL-E, Sora, they're all using diffusion model-based systems. So if you look at the process that diffusion models use, you have a text encoder which takes your question and converts it into a set of numbers that the diffusion model can understand. Then based on those parameters, it generates an initial image with a lot of noise. Then the model goes through this noise and refines it to get it close as possible to what you need it to be. And the training process, the model learns to add noise and clean these images. Model then learns to reverse this process. So some of the technology used here is things like stochastic differential equations, likelihood estimation. There's a few underlying technology behind that. But based on this, and most importantly, what we get with diffusion models is the ability to do a vast range of applications, from image generation, video generation, for creative industries, for research and development, and also accessibility improvements. Another type of generative AI systems are generative adversarial models, and these have actually been around for a few years now, where you train a model by getting two models to compete against each other, where you have one model which has the ability to decide whether something is true or false, and another model which is trying to fool it into recognizing, and that's how a lot of these models were initially built. Generative adversarial networks, or GANs, are a type of AI used to generate synthetic content, such as images, videos, text, and sound. So usually these systems have two parts, a generator and a discriminator, and they have an adversarial process where the two systems are trying to compete with each other. I'm just going through this on a very high level so that any of you who are interested now can go and learn about this. I don't have the time today to go into these in detail. If you build a GAN, and I built a few GANs over the last few years, and they are unbelievable bits of technology. The type of things that you can do with GANs are fascinating, from generating images to videos to, we've even been playing around with using GANs to generate synthetic data for training some of our other machine learning systems. And the training process is a generator creates a synthetic data, the discriminator evaluates the data, then you get some feedback, and then you try to see whether it's correct or wrong. And some of the key technologies behind GANs are the loss functions, which tell the difference between whether something is true or false, or whether it's a false item. You have the generator loss and the discriminator loss. But then using these GANs, most importantly, we use it for image generation, video generation, text generation, sound generation, computer vision, NLP. All these different types of applications are possible with NLP. Then you have what are called neural radiance fields, or NERFs. NERFs are used to generate 3D images from 2D images. Right? That's once again another type of generative AI technology, or a deep learning technology used to create detailed 3D representations of objects from 2D images. And now this is being heavily used in gaming, in simulations, anything virtual where you have to generate 3D models. And anybody who's developed 3D models knows how hard it is, how long it takes to develop any sort of 3D model. Now with NERFs, you're able to take 1 or 2 images of a particular object, and these NERFs are able to generate the 3D object based on that. And once again, if you look at the applications, you can do 3D model generation, simulation video games, visualization for robotics, Architecture and urban planning, scientific research, once again, the applications are endless when you take the applications of nerves. Then we also have what are called variational autoencoders, or VAEs. You all use VAEs already with a lot of the generative AI systems that you all do use. VAEs are a type of generative AI used to generate new data samples to a given set. And essentially what VAEs do is they are trained to encode certain parameters about a particular object or a bit of text. So what you have is, for those of you who know a little bit about neural networks, you start with a large neural network which has all the inputs, let's say an image, and then you try to minimize the size of the neural network, and then increase it again and train the neural network to be able to reconstruct the image from a lower level parameter space. And then if you cut it off in the middle, what you have is a bunch of parameters which are able to describe what was input at the beginning. And this has millions and millions of applications, especially when you're talking about creating encoding systems, encryption systems, reducing dimensionality of data, and most importantly for us, on how to create synthetic data. Once you have that ability, you're able to then generate millions and millions of synthetic data based on that. So VAEs are actually quite easy to build, but you need, once again, lots and lots of data to train them. But the applications, once again, are endless. You can use it for image generation, for anomaly detection, for data compression, scientific research, music and sound generation. There's so much you can do with these VAE applications as well. And the reason I'm going through this is that a lot of the focus these days is on LLMs, and I don't want students to only study LLMs. I want them to also look at some of the other generative AI technology out there. LLMs are amazing. It makes AI available to everybody, but the field of generative AI is much larger and much more fascinating than just LLMs. But LLMs are a primary component which make even things like VAEs available to normal people as well. And then once you put all these things together, what we've seen, especially over the last year, are the multimodal models, models which are able to do everything. Models which can handle text, images, music, audio, video, all at once. So a normal LLM is only able to take text and give a text answer. But a multimodal model is able to take text, a song, an image, and then output it in any one of those formats as well. And this is where, this is the type of models that now you're seeing on GPT-4o, Gemini. These are all multimodal models which are able to not only take text as input, but take other types of input as well, audio, video, documents, and all that. So in unimodal learning, you have a single input type and a single output type, but in multimodal learning, you have all these different types. And we are seeing so many different applications already on that. So multimodal models are essentially advanced AI models that can process and analyze multiple types of data, and they integrate different modalities. That's why they're called multimodal models. So anything from image captioning, visual question answering, video analysis, speech to text, audio-visual integration, all that's possible with these models now. So if you take, multimodal models are already in action. We are seeing them around the world. Facebook uses it for automatic alternative text descriptions. If you're an image, it generates that alternative text. IBM Watson has a visual question answering system which they built years ago. And for video analysis, YouTube uses multimodal models to know whether something's appropriate or not. But that's all gone now because now everybody has access to GPT-4, which is a multimodal model available to anybody. And you can input audio, video, text, documents, you name it, and you can output it in one of those formats as well. So usually the components of multimodal model are, you have some sort of encoder, modality encoder, depending on the type of input. It encodes it into a set of numbers. That's how computers understand this stuff. Then it's sent into an input projector, which is then sent into some sort of LLM backbone. You have an output projector, and then you output in the modality that you want. So the components of multimodal models are vast because it's not just one model, it's a bunch of models that have to be plugged together to make these larger systems. So obviously they have a large language model so that you can converse with it, you can interact with it using language. Usually there are diffusion models, you have GANs, you have neural radiance fields, VAEs. They all put together which make up these multimodal models, which is why I wanted to give you that background on this stuff as well. There's a little bit about MLOps and DevOps, which I think is a bit too much for today. I'll go through it, but MLOps, once again, MLOps and DevOps are essential for anything you do with generative AI and LLM systems, because that's the only way that you're going to build sustainable systems that can be continuously updated, fix problems, monitor them, just like any software system. You need MLOps and DevOps to be integrated into Gen AI systems as well. What I want to talk mostly about is some of the challenges and the ethical considerations for generative AI. Things like data encryption, access controls, and anonymization are very, very important because generative AI systems usually handle large amounts of sensitive data. So having a very, very robust data privacy and security processes in place is very, very important. So things like encrypting all data before you send it to the LLM so that people can't, there is no unauthorized access of your data, strict access controls, and also things like anonymization, if not done carefully, means that you'll be leaking all your personal information or your customers' information onto the internet for anybody to use. There are also challenges with bias and fairness in AI models, which are once again something that anybody developing an AI model or even using an AI model needs to understand very, very well. So things like making sure that your data is diverse, your training data is diverse, doing regular bias audits, and also having fairness metrics for your LLMs is very, very, very important. Generative AI systems also handle large amounts of sensitive data, which make a robust data policy very, very important. So you've got to be transparent, accountable, and you need to be able to collaborate. So if you look at some of the future directions for AI, what we'll have is continued development of these foundational models. We'll have more and more multimodal models coming in with the ability to handle even more varied types of inputs than they do now. And there's a growing focus now on AI ethics, and especially on ownership of data. I think that's going to be one of the biggest changes that will come over the next few years, where now it's been a Wild West where they've just been scraping anything off the internet and training LLMs. But I don't think that can continue forever. LLMs are coming to a point where every company's LLM is about the same. It'll come to that point in a year or two. But the differentiator will be what data you can train it on, who has access, who owns that data. So I think the big differentiator, so any of you investing in companies, invest in data. I think that's going to be the new oil, where these LLM companies will be buying this data now to train the LLMs. So we need more collaboration between academia, industry, and government. Research partnerships, industry consortia, and different government initiatives. So you really need to explore, but let me quickly talk a little bit about the national AI policy as well. We have a national AI strategy which hopefully will be launched in the next couple of weeks to a month. It's been a long journey. We've had about a year to develop this. And we've developed a very, very grounded strategy, but a grounded strategy where we understand where Sri Lanka is, and we have a roadmap for us to kickstart our journey. I mean, that's how we put it. We are nowhere in the world in terms of AI capacity. I think in global rankings, we are something like 95 in AI readiness in the world. So we don't want to put a strategy where we want to be number 10 in the world in 5 years' time. That's not going to happen. We need to start the journey, and the journey is a lot about, it's got two elements. One is we need to set up the foundational elements that the country needs. We need the skill sets, we need the people, and the skill sets going all the way across from the engineers, the hardcore engineers, to the business leaders, to the general users and the public. We need to train all these people at different levels. Very importantly, we need to have some sort of public infrastructure for training AI models, and that I think is a big problem for especially in universities, where it's just not affordable now to build models larger than a particular size, because it costs dollars, and there is no money available to do this. So how do we make some of this compute power available to the students, to companies? Then we need to create better public awareness. Sri Lankans don't understand how this technology is going to change their lives, especially how it's going to change their jobs going forward. And that awareness is very important. A doctor in 5 years' time, 10 years' time, there are going to be doctors, but they're just going to be working very, very differently. They'll be using these AI systems to help them. So if a doctor today follows the traditional route of becoming a doctor and ignores technology, it's those doctors who adopt technology who are going to be the better doctors in 10 years' time. It's the same whether you're going to be a lawyer, an architect, doing marketing. These technologies are going to become a big part of your lives. They're not going to replace these people, but they're going to have to learn to work alongside these technologies. So we have to create that public awareness as well. Fourth, we need to create a local R&D ecosystem. R&D ecosystem is very important because unlike other technology in Sri Lanka, where when we have a problem, we buy something from abroad and plug it in, that doesn't work with AI. Because with AI, it's got to be trained on local data to fit into the context. So we have to create an ecosystem in Sri Lanka where we are solving local problems. Not blue sky research, but blue sky research is important, but we also need dedicated facilities which are addressing some of the national priorities as well in agriculture, in health, and directly try to focus on those and not stop with publishing a paper, but how do we actually productionize it as well, make it into an application. So these are some of the areas we are looking at in the national strategy. Hopefully you will see this coming out in a few weeks' time. So let me end with that. Today's talk was just to set the groundwork, to explain to you what generative AI is and what this landscape is about, and some of the viewpoints on how we are seeing this in industry. Thank you.
Dr. Ramesh, could you please remain on stage? Now, I would like to invite Dr. Ruan to present the token of appreciation for Dr. Ramesh.
Moving on, we're now pleased to introduce our invited speakers, Professor Nirmali Veeratunga and Dr. Stuart Massey from Robert Gordon University. Professor Nirmali Veeratunga is a professor in intelligent systems at RGU's School of Computing and the Associate Dean for Research. With over 2 decades of experience in computer science and AI research, she has held positions such as postdoctoral researcher on EPSRC-funded projects, was appointed reader in 2009, and became a professor in 2016. Professor Nirmali is also an adjunct IDUN professor at the Norwegian University of Science and Technology. She leads the Artificial Intelligence and Reasoning Research Group in the School of Computing. Her extensive work includes developing human-centered AI platforms for explanation, strategy recommendation, and using case-based reasoning for retrieval of augmented QA systems with LLM. Additionally, she co-founded Adenta app, a mobile attendance tracking solution for students and conference attendees.
Dr. Stuart Massey received his PhD in 2006 from Robert Gordon University, focusing on knowledge management for case-based reasoning systems. He currently serves as a reader with the Artificial Intelligence Reasoning Research Group at RGU. With over 15 years of research experience in AI, Dr. Massey specializes in developing advanced machine learning, information retrieval, recommendation, and data mining technologies. His research, wide-ranging applications from text and multimedia to sensor networks, aiming to create applied solutions, Dr. Massey has an impressive publication record with over 90 peer-reviewed papers in esteemed journals and conferences such as the Artificial Intelligence, ICIIT, and IIIT. He also contributes as a program committee member for various international conferences, including KSEM, ICCBR, ECIR, EANN, and IJCAI. Please join us in welcoming Professor Nirmali Veeratunga and Dr. Stewart to deliver the invited talk.
This one, then Stuart side. Make a Isella, it was a devani.
Open this one.
Oh, make this one first. Use this. What's this for? Right, okay. Good morning, everybody, and sorry for that slight delay. Stop and reset. Right, so I'll maybe talk for about 25 minutes, and then I will hand over to Stuart to take it over from there. So what I'm going to talk today is an area called case-based reasoning, but what I'm going to look at is how to combine the certain capabilities of case-based reasoning with large language models. I think Ramesh was talking about the need to be able to take large language models and sort of adapt it or personalize it to companies in a rather rapid manner. And we believe that RAG, retrieval augmented generation, is one of these methods. And what I'm proposing here is that case-based reasoning is a very valuable paradigm that can help in that task. I don't think the screen is showing. So what the screen is supposed to be showing is a quick overview of the talk, and I can just tell that to you while he's fixing it. What I'm going to talk about first is to give a very quick overview of how a large language model on its own has a lot of pros, but it also is lacking in certain ways, and I want to just spell out some of those things first. Thereafter, I'm going to talk about how this retrieval augmented generation technique can be integrated with large language models, and there are sort of 3 key steps to doing that. One is the step of taking existing corporate knowledge and embedding it in a format that allows us to retrieve the most relevant content from corporate knowledge. So I'll talk about how to embed it, how to retrieve it, so that you can integrate it into a LLM prompt. That integration process is what causes the name augmentation. So retrieval augmented generation is the idea of taking that relevant knowledge and embedding it and putting it into a LLM prompt. I don't have a lot of time to talk about the legal Q&A study that we are currently doing with RGU, Informatics, IIT, and also some of our partners from BT France. But I will sort of use some examples from that as I go along to showcase some of the ideas. So I would argue that transformers is probably the best idea in AI. I think some people might disagree, but as Ramesh was talking about the transformers, that ideas came in this paper called Attention is All You Need. And the title of that paper is so, what do you call, laid back. You wouldn't even think it's making a big statement. But that is the paper that actually presented transformers. And I don't know if at that time those authors knew the amount of impact they were going to make in this field. So 2017 is when this Google paper came out, and that's where they spell out how to use self-attention and the basic architecture system. And what is clearly amazing about transformers is the fact that you can use that same architecture on text, video, speech, time series data, or anything. And often they talk about this architecture as being a general purpose, differentiable compute. And I like that phrase to describe it. It comes from Androjet. And what they say is that it is expressive in the manner it can take the forward pass with the positional encoding and so on. It is optimizable because everything can be back propagated. And it has this inbuilt technique where, for example, when you put data, whether it's tokens or whether it's parts of pictures, if you have a big image and you break it into small areas, you can put all of that in parallel, and that gets processed at once. So that makes it quite efficient piece of block of architecture as well. I don't need to emphasize the impact it has had. I think a lot of that was mentioned by Ramesh, but I think we would by now agree that large language models are used everywhere. In fact, quite a lot of the projects that we are getting called to do in the university with companies is all about how do we use large language models on our particular task, whether that is using their existing corporate knowledge or taking an existing general purpose language model and personalizing it to their companies. So if you look at the pros and cons, we often see a typical ChatGPT as a very good front end because it is very good at taking language and making it very fluent. And this was one of the problems we always used to have with natural language generation and processing, is that no matter how much you put computers to do something, the final output used to be a little brittle, or it seemed a bit artificial. But as soon as you now throw a GPT in front and use it as the language interface, it looks very fluent and it looks very interesting, and it talks almost like a human. So I think that's a real strength of large language models. And the fact that it has been trained on almost all of internet, I guess it has a very generalized knowledge, good common sense knowledge. And in AI, we had lots of problems in getting models to have common sense knowledge. It's not solved yet, but it has gone a great length to try and resolve this problem. And as the first invited speaker said, LLMs are going to take away a lot of our routine tasks, whether it's, helping with grammar checks or whether writing something, even taking standard text and from a meeting and say, create me the minutes from the meeting, it will do that. So small tasks like that are all becoming very easily automated. But one of the problems is how do you personalize or fine-tune it to your own data? So I think that is an area that needs further attention. And that leads to some of the problems or the disadvantages we currently face with large language models. So to fine-tune, you need a lot of data and resources to do not only have the data, but also to do the fine-tuning. It still lacks accuracy if you just use an existing large language model and try to use it on some kind of a specialized task, whether it's law, legal, or pharmaceutical, or engineering on a specific task. It can still, as we say, hallucinate, and it's not factually accurate. So these are problems that we are trying to address, and one of the techniques that we want to do is retrieval augmented generation, but there are other alternatives as well. So this particular paper talks about training language models to follow instructions with human in the loop. So this is one way of personalizing or fine-tuning a large language model to your corporate data. And what they do is they emphasize the need to bring in a human to do the instruction. So from GPT-3, when we sort of moved to GPT-4, a lot of the step change was due to this type of technique where humans were brought in to do what we call instruct GPT technique. So the key idea is earlier we didn't involve humans, but here by involving humans in the backpropagation, what they are able to do is have reinforcement learning with human-provided judgments. And the other technique that we have used recently is the retrieval augmented generation. So I'll very briefly cover this RLHF technique. It is difficult for us to do that because you need to have access to lots of humans to try and give supervision and instruction. But in the absence of that, the retrieval augmented generation seems to be a far more easier technique for us to adopt if we have corporate knowledge in terms of reports and documents and so on. So the RLHF technique, which has led to GPT-4, has three basic steps. The first one is that they would have, from a random sample of prompts, they would select a prompt, and they would ask a human to provide give an instruction as to how to solve that particular prompt. That knowledge is used and maintained. So imagine you have thousands and millions of humans giving supervised data for how to solve a prompt. That data is used then to train a model. Then in the second step, what they do is they get the prompt and they get alternative solutions from a model, and they ask the human to rank which solution do you think is the best one and to give some ranking. So they collect that knowledge, the ranking knowledge, and create another model. And so what that second model allows you to do is, if a LLM provides a particular response, it is able to say to what extent is it good. So that relevance judgment is useful, and that is kept as a second model. And then the final thing that they do is they have a whole lot of prompts that have not been used in the first stage, but they take that initial model that we had in the first step and they start to try and refine it by using new prompts, getting this partially trained model to generate a solution. Then they use the human trained model to say, how good is this solution? And based on that reinforced learning technique, they are able to refine what the entire model that they had in the first step. Their research suggests that with I think about 1.3 billion parameters as opposed to 175 billion parameters, they found that their instruct GPT with the human model gave far more preferences. Humans preferred the solutions from the 1.3 billion compared to the 175 billion. So they have made a huge impact in GPT-4 to get to that level with a small amount of parameters. But as you can say, the problem here is there's a huge labeling cost. You need lots of humans to help you do the human in the loop learning. So that second technique that we are exploring with IIT is this technique called retrieval augmented generation. So we will go through that very briefly because it's a very straightforward technique and most companies can adopt this. So if we take a very basic large language model, what happens is you have a person with a query or a prompt. They send that prompt into the large language model and you get your answer. That's the standard sort of process if you use ChatGPT. So the way this technique changes is, so this is the previous picture, but it adds a little bit of extra steps. What happens is you get the query, and then from your corporate knowledge or your whatever the database that you have, you take that query, embed it in a certain manner that you can go to your database, retrieve the most relevant information, rank that information, pick maybe the best one or the best three, combine that into your prompt. So you have your query and your context from your company database, if you like, put that together and present that as your new prompt to your large language model. And that sort of gives a new answer, which is more contextualized to your specific domain. And so this is this alternative mechanism to rather than using human in the loop training. So some of the challenges here involve how do you take your query and embed it in such a way that you are able to retrieve the right company documents. And then if you want to retrieve the company documents, and let's say these documents are structured in a manner such that they have different parts or subsections, how do you take that query that you initially have and map it to those subsections? Because if you do that mapping correctly, you will find relevant documents or relevant context to your query. So those are the two areas that we focus in our research, how to embed it and how to match to different sections. So if we look at the 3 steps, for RAG, we have this step of embedding, how to do that. Retrieval, how to do retrieval. Of course, you can do a straightforward database, SQL or something, but what we found is some of the techniques from a methodology called case-based reasoning is very relevant here, and our own research shows that if you use these types of more fine-grained methods of matching subsections of documents, you get better retrieval. And thereafter, the 3rd step is how to combine the context with the query to generate the text that you need, the answer that you need. Just checking my time. Right. So with regards to embedding, we have, you have the text, you send it through some model that helps to embed that text, and embedding is nothing but a whole bunch of numbers, right, as we can see here. There are a variety of different language models, as mentioned by the previous invited speaker, that we can use to embed. So standard techniques like BERT will take your text and encode it. It has been learned in such a way, BERT, by looking at a masked model technique. So you mask certain tokens and see if you can predict that mask, or you give it 2 sentences and it tries to see are these sentences adjacent or not. So that's how it has been trained, and sometimes that training strategy might not be truly aligned to what you want when you are trying to embed your questions, because maybe the questions that you're asking may be better off with a model that was more aware of similar documents, which would be then able to take your question and embed it or provide it a representation that helps it to identify things that are more similar. So there are certain models called metric learners which can do such a job, where it has been pre-trained to be able to identify things that are more similar. And so what we did in our research is to compare embeddings from a standard straightforward embedding technique, self-supervised technique like BERT, which is only based on masking, and then exploring embeddings that are being used by models that are a bit more aware of similarity information. So looking at these metric learners, such as this Angle, what it does is, when it has been trained to try and find a particular piece of text, let's say anchor text, and it's given 2 other alternative texts, such as a negative text and a positive text. So a positive text is something that is very similar to an anchor, and a negative text could be a document that is very different from an anchor document. And when given these triplets, as we call them, 3 three things. Through the training, the model will try to bring together the positive document, the documents that are alike, and push apart the documents that are further away, push them because they're not close enough. So by taking these triplets and learning for a long period training, what you end up is a model that is able to take your text and embed it in a manner that is helpful to identify things that are similar. Right, so key to getting this right is to identify how to find those triplets to fine-tune or train these models. And often what we do is, given a, let's say, collection of documents, in this case we used Supreme Court cases, we did a semantic chunking of them, tokenized, broke them into sentences, and then used a straightforward BM25 similarity measure to try and identify sentences that are similar lexically and sentences that are not so similar to form these triplets. And once we find these triplets, we can then train one of those metric learning algorithms to give us the embeddings that we need. So once we do the triplet construction, there are some interesting types of loss functions. I don't want to go into that here, but you can combine different types of loss functions to get alternative, let's say, aspects that you want to optimize against. And then what happens is you get a fine-tuned embedding, an embedding that has been fine-tuned on your document, on your corporate document, or in this case, Supreme case PDF files. And we can use that model to generate, given a question, to generate an embedding that is relevant to that particular domain. We also do two other things. We explored two flavors of these fine-tuned models. One was a model that can create an embedding to find other documents that are in, let's say, the same vocabulary. So they are in the same vocabulary and therefore can find exactly sort of similar types of documents. We then had another model which tried to take a query and place it in an embedded space where it can be matched with other documents that may not necessarily be in the same, let's say, vocabulary, to find a better word, as the initial query. So the query is kind of adjusted in a space that makes it possible for you to compare it with different sections in a court case document. So we had these two flavors. With that, armed with that, what we did was we used case-based reasoning to retrieve relevant documents to augment the prompt to get answers that are more relevant to a question. So this was the general pipeline. We have a log document in PDF, and we obviously want to create some kind of a structure so that it can be put into the case base. So we decided we will have a question, we have some support text, entities, answers, maybe and the answer as well, and the legal acts. So these are things that already exist. And there's a semantic chunking process. You need some prompts to generate and extract the entities. But nevertheless, through that process, what we have is a collection of a potential question, some representation, and some answers, and we keep that in our database or case base. Then the next thing we do is we want to take that case-based database cases and embed them. So we take the question, we embed it in a certain manner. We take the support text, we embed it in a certain way. And because we have these two models, we can give it a different flavor depending on what it is we want to match. So just to summarize, when a person comes with a particular question to the LLM, we convert that question into two flavors. We go through our embedded case base, and we are able to retrieve cases by matching these embeddings based on what it is that we want to do. This matching and doing it very quickly, what we adopt is a architecture that we have built in our research group called CBR. This is a microservices cloud-based implementation, and it is very scalable, and we've used it in many of our projects with companies as well. It's easy to use, it is API based, but importantly, it comes with a whole load of similarity metrics that are already there. So given different attributes, you can figure out what similarity measures you want to improve your retrieval technique. So if anybody's interested to try it, I have the QR code there. I can give it to you later as well. So just to summarize then, we are able to retrieve relevant content when somebody comes with a question. We can take the retrieved content and put it into the query, and that augmented query becomes part of the prompt that goes into the large language model. So this is the sort of the pipeline then. A human comes with a question. We sort of identify from the question what is relevant. The case base gives you the important text. We take the text, create it into a prompt, and then give it to your favorite LLM, whether that is Mistral or Llama or whichever it is that you want to have, and that then generates the answer. So did it work? Well, we did a paper recently which got published, and it certainly did give us better results. We found that using this retrieval augmented generation with the metric learning models rather than the vanilla flavored BERT models leads to superior performance. Therefore, our final thinking so far is that contrastive learning based embeddings is vital to get the correct cases, and also having the cases structured in subsections and finding different ways of matching those subsections is important to improve accuracy. At the moment, what are we doing? We've created a survey that we are sort of sharing with people in the legal experts to try and find out what types of questions might they want to pose to a legal question answer system, so that we understand, first of all, what is their intent, and once we know their intent, we can look at better loss functions to improve our embeddings to help the retrieval augmented generation LLM technique. So that's our team who are involved in the research paper. So I want to say thank you to them, and I'll hand over to Stuart, who's going to talk about another use case of how to integrate case-based reasoning with large language models. So we can have questions later.
Okay, yeah, thank you. So I'm conscious we're probably a little behind time and got the slot of keeping you before coffee, so I'll try and be reasonably brief. So when you normally ask me to sort of talk a little bit about what we've been doing with the CBR, case-based reasoning, and the data-to-text problem and text generation, at this event I thought, well, it's relevant, it's not really a great fit. So the work we've been doing probably finds that certainly end-to-end generative AI systems don't really work for us. And this is more, we certainly use LLMs, but we use it more in a pipeline than the typical way of using it in an end-to-end approach. So maybe it's a little bit break on the enthusiasm we've had so far in identifying some of the challenges with using it and some of the problems with using the end-to-end approaches. And maybe takes us down to earth a little bit on some of the enthusiasm that's going on around about generative AI. So a little bit, you heard this earlier, so I won't talk in any particular parts here, but I've been working in AI for probably close to 25 years, 24 years in different versions, and sort of focusing very much on case-based reasoning through that time, knowledge representation.
And there's been lots of ups and downs over sort of the 25 years. And probably there's a lot of dark times early on, and it's only recently that there's been a coming together that AI has something to offer. Industry's really enthusiastic about it, and we've at a sort of peak with both sides being massively enthusiastic, and that this is a new way going forward and going to be sort of transformational. And hopefully it is. I have seen previous versions of this, but I do think this is the real one, and it is going to be a massive difference. So we'll sort of outline what I'm going to talk. I'll go through these quite quickly. I'm going to talk to data text generation problem, exactly what this problem is. I'm very much application focused and focusing on solving specific problems by the best means of doing that. So I'm looking at our case-based reasoning approach to it, why it doesn't work, looking why the generative approach didn't work, and doing a bit of analysis of that problem, and then identifying a pipeline approach that incorporates LLMs and gives us a solution that does work, but has downsides in that it's very domain specific and it's less flexible than the approaches we'd want. So, data to text, it's sort of one of many problems around about text generation, but its the specific side is we have an input as a set of data. That set of data can be lots of different things. Normally this data is structured data, so it's numbers, and it might be weather forecast data. It could be, in the situation here, in the examples I'm going to talk about, we're talking about robot journalism, and we're talking about sports reporting, so creating sports reports in text from data going in. So there's lots of use cases for this, used widely. Financial reporting from financial results, create some text that's engaging and different but also accurate. And in all these use cases, medical probably a typical example, but in virtually all these use cases, the number one thing that has to be is correct. It has to be accurate. It can't make mistakes. I think there's been a bit of laxness maybe around about or over-enthusiasm around about auto-generated text. It is really fluent. It appears absolutely human-generated, but it's very easy to forget it makes an awful lot of mistakes. It hallucinates. And in virtually all these use cases, there can be virtually no hallucination. And that's why at the moment, they're virtually all solved in industry using template approaches, not using auto-generative approaches. And that's the challenge, is to get auto-generative approaches to the level that we can use them without having to produce these custom solutions. So the data to text problem at its simplest, we've got some text sort of input, or some numbered input going in, and we're going to produce some text report. In this example, we've I think it's basketball games we're going to focus on for this example. So we've information about the teams, information about the players, and then we're generating some text. So from that perspective, it is a relatively simple problem. And there's two main solutions. One is the end-to-end generative solution we're talking about here. And if you look on this diagram at the right, you see it's really good at making diverse text. It's very human-like, but it has the problem it's not as accurate as we need. The other approach, rule-based approaches, at its simplest, a template that's got slots to fill in the values. It can be much more complex than that. They produce accurate values, accurate text, but they're not engaging, they're not human-like. So that's the trade-off. We've got this template rule-based approaches that are accurate and we can use, but are not very engaging. We've got auto-generative that are really engaging, but make mistakes that we just cannot allow. And the challenge is to get to this ideal system that doesn't make mistakes, but is engaging and diverse. But the problem actually, when you start looking at it, becomes a bit more complex. So most reports that we look at aren't just looking at a specific event. So the basic sort of challenge of, we've got the current game event, let's write a report on it. That's not what reports are like. The reports are aware of the context and the world round about it. So when we're writing this report, we need to be aware of the context. We need to know about the previous games the teams have played. We need to know where they are in the league. We need to know the other games that have happened at the same time. So we need to know information really about all the games that are happening. We need to know them happening this year. We need to know about them happening back in history over the last, what happened when these teams played over the last 10 years. We need to be able to bring lots and lots of data that is in a very diverse spread about into one place and produce this report. And that's where the problems come when we're using auto-generated. The data is just too diverse, and bringing it together to get these accurate reports is really difficult. So it becomes more complex than this. We have some teams are more popular than others. Some players are more popular than others. So you have to write about some players but not the others. Even if another player has done better in the game, you still have to write about certain popular players. So there's perceptions about what you should write. There's positions in the league. What time in the season is it? If it's the end of the season, you have to focus on league positions. Beginning of the season, you're focusing on other things. So there's these contextual, environmental contexts going on round about it. At the same time, with writer style. Different organisations, different newspapers, whatever, will write in different styles. And you have to be able to capture that style when you're producing the generated report. So all this has to come together. And it makes it a much more challenging problem than it sort of first appears. And it's similar, this is sports reporting, it's similar in financial reporting, it's similar in many other areas. So our first attempt, case-based reasoning, by background, first attempt was to do that. We compared the case-based reasoning approach with auto-generative approach and template approach. So the case-based reasoning approach, we take all the data we have, we split it into a case structure, so we have a problem side is the data, solution side is the text. We look at the reports, and we actually did some domain-specific stuff. We looked at the structure of reports and said, okay, we can create a structure, so we have a semi-structured report now that we're going to produce. It's got a bit on winning team that won, it's a bit about the team, it's a bit about the player, and it's a bit about the next game. So this is sort of our first approach, case-based reasoning approach. Case-based reasoning, 2 stages. We build a case base, then we use that case base. So in building the case base, we have sort of 2 stages. We take the texts, we use semantic similarity, we cluster the text, and form the text into different sentences. We cluster those, identify ones about teams, ones about players, ones about the next events, and we'll take these different clusters of text. We generate templates from them by filling out the named empty recognition, we fill out the slots, and then we have our case base. So the case base is all the previous reports with templates generated associated with that game with slots that we can then fill in. And we've done this for each sentence in the report, so we've broken down the reports into sentences, and we can then start working with generating a new report from this case base. So we built our case base, we now have a new game we want to report on, we get some new data in, so we have some similarity matching, we weight the features, we do some entity selection for the different components of our summary, we retrieve a number of cases that are going to be relevant. So by using case-based reasoning, we're getting relevant templates without having to build the rules system. That's the benefit. We cut down on this knowledge engineering part by just using the data we have and build these templates. So that works really well. We use a language model in here to choose which template we use. We use perplexity score, so how good is the text, how fluent is it? We choose the fluent one based on our language models, how close it is to the language model output. And then we fuse these together to generate some text for our summary. All works really well. Got, to some extent, very good results. Just in terms of highlights, it's more accurate certainly than the auto-generated. It produced accurate results. That was great. It wasn't as fluent as the auto-generated, but it was certainly much more fluent than the template side. So we got a reasonable solution. and we're sort of happy with that. We're using LLMs. Maybe if we started this now, we started this a few years ago, we would have a different approach. But it certainly worked quite well. A couple of publications there, the code's there in GitHub, and we wants to follow up on it. But when we looked at a bit more detail, we found we were really good on some of the content, but really bad on some of the other content. And it goes back to that diagram where I say we've all this context round about the other games that are going on, what time of year it was. And when we came to that kind of content, we found that, well, actually, we weren't very good at that bit. We were really good at the bit about the game that was captured with the game data, but we were really bad about the other stuff. Auto-generated stuff was good about some of the stuff about the game, but only so-so, and it was even worse about the rest of the stuff. So we started analysing the type of reports and say, well, how can we look at this, how we can break it into parts. So we then had different type of sentences that were in our reports. Some were just straightforward from the game, reporting a piece of data that's our input data, filling, if it was a template, fill a slot, this. So within the event, and it's a basic bit of content. So that was one type. Next bit of content we had was, well, it's still within the game event, but it's actually calculated. A bit of arithmetic's going on to calculate or infer the value. Maybe you had Team A scored 110 points, Team B scored 90 points, they've won by 10 points. You had to calculate that 10 points by doing arithmetic, take one from the other. This is where the CBR system did well. The auto-generated did terrible. It wasn't very good at arithmetic. The template approach did fine because we created a rule that solves that for it. So, but that was certainly a challenge. And then we come to the next bit where the systems were really terrible. This is where we're taking events from previous games. So this might be highest score in the last 5 games, or they've averaged the score, the players averaged 20 points for the last 3 games. So you need to know the past games, you need to do some arithmetic, and you need to put it all together into a sentence. Both approaches were really terrible at doing this. But looking at this typology was actually really interesting. That's the diagram of how we created the typology. We started with a few label examples, using machine learning, active learning, and a machine learning approach. And we classified all the sentences in our data, and we came up with a profile that highlights the content of a particular data set. And we found it made up with, here's for 4 data sets, and we look at the proportion of sentences, whether they are just this basic content, whether they have complex content from the event, or whether they've content from across other events. And we found some data sets. Actually, the first thing we did this was obituaries. Our obituary solution worked really, really well. Spinout went and took the system. But when you look at obituaries, they've got no data from other events. They're all captured within the event, and that's why our system worked really well. So given this sort of distribution, we were working with the second one in there, where 66% of the sentences were basic information, but 65% of the sentence also had calculated information, and 30% of the had things from other events. And that 30% we were getting terrible results on. So that was the challenge. Another interesting thing came out of this. We looked at, our data set was actually split into training data and test data. They'd done it by year, so the first 3 years was training data, last 2 years was test data. There was actually different authors for the different periods. And so the training data had one profile from author A on here. The test data had the profile from the second author. And so the task they'd actually given was really, really hard because the data didn't reflect the two. And it was amazing how easy or how obvious it made that from this simple evaluation. So it was actually really effective. Again, publication there if anybody wants to pick up on it, the code's there as well. So I'll just finish really quickly on the approach we did come with, which is a pipeline approach. So again, case-based reasoning approach, but more going to auto-generative. I'll just go with the diagrams, I think. So the first part was we split the task into 2 parts, creating a plan, producing the text, creating the plan, and so I've got a plan being created here. We take each sentence, we identify the sentence. Is this type basic? Is it type complex? Is it a combination of the two, and what entities does it talk about? So does it talk about teams, does it talk about players, does it talk about teams and players? So we had these different parts, and we created a plan that each sentence that we were going to produce in our plan had this type of content. So ensure we got this content from other events being embedded into our system. So we had the right profile, we had a human-like profile in the finished summary, and we could choose which humans type profile we were going to produce. We could produce author A or author B's, and we could produce their profile by using their data. Then simply use the CBR approach to user input data. We have our case base of now data and plans rather than data and templates. We retrieve our plans, and that's the first stage. The plans retrieval stage worked really well. The plans we retrieved were very like human-like plans, so that side was fine. We then come to the second stage, which is the realization. So here we went back to a more standard auto-generated approach, but we generated on the fly a database of the information we needed to do the content from the other events. And that really was sort of how we managed to solve this. We have our content plan, we populate this content plan, but we make the data available that's needed to populate the plan from the other events. We used an auto-generative approach, worked pretty well. We actually did some post-editing with our CBR and used a combination of the two and produced sort of really good results from this. It worked very well and produced pretty much human-like outputs. We did a human evaluation on it. Again, there's a publication there that highlights that. But we were able to create generative summaries with accurate content and very human-like. So that's the good side of it. The downside is we still had domain, it was a custom solution. So we had domain knowledge, and we had to sort of generate this individually for each solution we were going to do. So that's the problem. So the challenge going forward then really is, how do we do this but without having the domain-specific part? I think there is lots of potential at the moment. So RAG certainly brings up potential for generic approaches that are going to solve this. But at the moment, I think it's a challenge rather than a sort of solution. Okay, I think that was me. Thank you.
Thank you, Dr. Stewart.
Ladies and gentlemen, now it's time for a brief tea break. Afterwards, precisely at 11:30 a.m., we'll kickstart our 2 breakout sessions. So track 1, focusing on industry applications, will be held in this same room, room 7LA, and track 2, centered on neural language processing, will take place in room 7LB. Thank you, and please proceed to floor 8 for tea and refreshments.